Frame ABC is supported in part by a cable DBE. Note that passes through a frictionless ring at B. Knowing that the tension in the cable is 385 newtons, find the components of the force exerted by the cable at D. So we want to know the force here at D and find that force, D. We know if the cable is continuous between D and E and through that ring at B, and that the ring is frictionless, that the tension in the cable is the same 385 newtons no matter where I am. This is the force at D, this one is the force at E. But that the cable, the tension, no matter where we are in that cable, the tension is 385 newtons. It has to be that, otherwise the cable would be moving until it comes to some kind of static equilibrium. But once it's in static equilibrium, then throughout the cable, the tension is the same. To find the force at D, which we're looking for here, so we're going to look for the force at D, which is a vector. We're trying to find the x component, the y component, and the z component of that force at D. So the first step we're going to do is to try to find the vector at D, and to do that we need the coordinates of the endpoints. So we want the coordinates of point D. We start with that, and the coordinate of D here along the x-axis it's 0. There is no it's on the YZ plane, so the x component of D is 0. The y component of D would be this measurement here. It's looking at along the y-axis, D is 510 millimeters. And then along the z-axis would be this measurement here. And how far along, following the z-axis along, how far along are we? And that would be 280 millimeters. Point B is the other end of the vector, or the other end of our line for the vector BD, or DB. And so we want to find the coordinates of point B here as well. So along the x-axis, we would find this measurement here, 480 millimeters. Oops, lost my 0, 480 millimeters. The y component, we can see we don't, there, it's in the xz plane, so there is no y component. And then the z component would actually be this measurement here, or 600 millimeters. So to find our vector, the vector we want, we're starting at point D and we're going towards point B. That's the direction of our vector here. If we start at D and we go towards B, this is the notation we want. And when we have this notation, then we know that we subtract the coordinates of B, we subtract the coordinates of D from B, or B minus D. It's final minus initial. So our final point minus our initial point to find that vector DB. So DB, we would find, we take the coordinate of B and we subtract D. So this would equal 480 millimeters minus 0, or 480 millimeters I. And then the next one, the J component, we have 0 minus 510 millimeters. So it would be negative 510 millimeters in the J direction. And then for the Z component of this vector, we have 600 minus 280, which would give us positive 320 millimeters in the K direction. So there's our vector D, our vector DB, the vector starting at point D and headed towards point B. Next thing we do is we find the magnitude. So we're going to find the magnitude of our vector, the magnitude of dB vector. And to do that, we use the Pythagorean theorem. And we can use this notation, the magnitude. We use sort of the absolute value marks of dB to indicate that is the magnitude. And we're going to take the square root of 480 millimeters squared plus negative 510 millimeters 510 millimeters squared plus 320 millimeters quantity squared. And I don't know why some of my lines are not working out today, but you get the idea. So then the magnitude of this vector would be 770 millimeters. And so there's our magnitude of our vector. So now we can find the unit vector, lambda. That's what we're trying to do here. So lambda is the unit vector of the at D or of the force vector at D in the direction, and indicates the direction of that force. To find the lambda, we take our vector dB and divide it by the magnitude dB. So this is going to be 480 millimeters I minus 510 millimeters J plus 320 millimeters K, and all of that divided by 770 millimeters. I'm going to move this over. So this equals 770 millimeters. If I try to increase my thickness, if that helps. It didn't make any difference. So that would be our unit vector. Then we know the force at D is going to equal the tension in the cable at D multiplied by lambda, the unit vector. And so this would give us, the tension is 385 newtons, and we're going to multiply that by 480 millimeters in the I direction minus 510 millimeters in the J direction plus 320 millimeters in the K direction. All of that divided by the unit or the magnitude, which is 770 millimeters. And this would give us then our final, maybe I will try a different color. Let's try, let's go back to just using black and see what happens. So then our force at D is going to equal, multiplying this out, our force, we can say dB, D in the direction of B, is going to be 385 newtons, because this is 300 and, no, it's, yes, 300, well, sorry, this is a mistake. 385 newtons, these are all millimeters divided by millimeters, so our units will be 385. Our final thing here is 240 newtons in the I direction minus 255 newtons in the J direction plus 160 newtons in the K direction. And this is what they asked for, actually. They asked us to find the components of the force. So Fx is going to be 240 newtons. Fy is going to be negative 255 newtons. And Fz is going to be 160 newtons. Those are the components of the force exerted by the cable at D. The components of the force exerted by the cable at point D. And we could do the same thing for the forces at point E.